Hi all, a very good day to all. Myself Kartika, Assistant Professor, Computer Science and Engineering in Banariaman Institute of Technology. Hope all are doing well. Code generation. Code generation is the process by which a compiler's code generator converts some internal representation of the source code into a form of machine code as represented in this diagram. Our code generator is highly machine dependent and optimizes the generated code, and also it gives efficient and correct code with high quality. So this figure depicts the role of code generator. See where code generator is present. Code generator is present between front end and the back end, that is the target code. Code generator is responsible for producing the target code. Before code generator, we use optimizer, and this optimizer is used to optimize the code to be generated. Okay, so it tries to remove all the unnecessary blocks of code, and it produces an efficient and faster running code, and that code is provided to the code generator, which in turn generates the target code. So the target code is the output of our code generator. So the input of our code generator is nothing but an intermediate code, that is the 3 address code, and output is nothing but a machine level language or assembly language or a relocatable language, that is our target language. And let us see what a good compiler should be. What are the conditions a good compiler should hold? First, the output code must be correct, that is the meaning of the source and the target program must remain the same. The meaning should not change. That is, given an input, we should get the same output both from the target and from the source program. We have no definite way to ensure this condition always. And the next condition is output code must be of high quality. It means the target code should make effective use of the resources of the target machine. That is mean by a high quality output code. Then a code generator must run efficiently. So it is of no use if the code generator itself takes hours or minutes to convert a small piece of code. So always a code generator must run efficiently, quickly, right? Next, we are going to discuss about the various issues available in the design of code generator. So these issues depend on the target language and the operating system. These are the issues to be considered while designing a code generator. The first issue is input to the code generator, target programs, instruction selection, memory management, register allocation, and evaluation order. First issue, input to the code generator. The input of the code generator is nothing but the intermediate code of the source program together with the symbol table. So this is the input given to our code generator. And along with that, we need to provide the runtime addresses of the data objects. Okay, so the intermediate representations are usually 4 types. One is linear representation, nothing but postfix notation, 3 address representation, that is our quadruple representation, and virtual representation, that is our stack machine code, graphical representation, that is our syntax tree, and DAG. So these are the various representations of our intermediate code. So the first issue provided to the code generator is nothing but its input. How the input is provided to the code generator. That is the first issue to be dealt with. Next, target program. What is target program? Target program is nothing but the output of the code generator. So the target program may be an absolute machine level language or relocatable machine language or assembly language. What is mean by absolute machine language? So absolute machine language is nothing but it can be easily placed in a fixed location of memory and it can be immediately executed. Example for absolute machine language is PL language or C language, and absolute machine language is also faster for small programs. Then relocatable machine language. So relocatable machine language program allows its subprograms to be compiled separately. Okay, so the set of relocatable object modules can be linked together and loaded for execution by a linker. So For the execution of relocatable machine language, we need what? We need linker and loader. Next, what is mean by assembly language? Assembly language can be easily generated by the code generator. The assembler has to be used for executing this code. So assembly code requires assembler, linker, loader and macro processor. So these are the types of target programs. So depending upon our machine, depending upon our hardware architecture, one of the target program will be produced by our code generator. Next issue to be considered is memory management. See, always the names in the source program has to be mapped to the addresses of the data objects in runtime memory. After mapping the names in the source program to addresses of the data objects during runtime, the machine code will be generated accordingly. So labels in 3 address statements also have to be converted to address of instructions. So these are the memory management things that is handled by our code generator. First is the names, the variables that are used in the source program has to be mapped to its addresses. After that, only machine code will be generated. Then along with that, the labels present in the 3 address code has also be converted to its respective register level instructions. Next, instruction selection. The nature of the instruction set of the target machine determines the difficulty of the instruction selection. So always the instruction selection is a difficult task, and some important factors are to be considered while selecting the instruction, that is uniformity and completeness. So these two of the instruction set are important factors, and instruction speed is also important. So these 3 factors are necessary while selecting an instruction. For example, say x is equal to y plus z. So this is a simple expression. How this expression is converted into an assembly language? So first we need to move y to the register R0, then we need to add z to R0. Because the register R0 will contains now the value of y, with the value of y, the value of z has to be added. So that is the meaning of this instruction, add z comma R0. Now what R0 contains? R0 contains addition of y plus z. So that result has to be transferred once again to x. That's why we write another move. So move R0 comma x. So this helps to assign the value present in our register R0 to x. So this is a simple instruction set that is selected for performing this expression. So the quality of the generated code, this is the generated code. So the quality of this code is determined by its speed and size. The cost difference between the different implementations is also significant. See, for example, a equal to a plus 1, a normal increment operation. Okay, so for performing this operation, the target code for this expression would be, first we will move a to the register R0. So the cost for this move operation is 1. Then what we will do, we will add 1. 1 is nothing but a constant value. That's why we are using a immediate representation hash. So we will add hash 1 with R0. Now R0 contains the value of a. With that value we are adding 1. Okay, so for the cost for this addition operation is 1. After performing addition operation, finally the result that is present in R0 has to be moved to where? Has to be moved to a. So once again a move operation will be written. So move R0 comma a. So for this move operation is also the cost is equal to 1. So what is the total cost? 1 plus 1 plus 1, that is equal to 3. So the total cost needed for this simple increment operation is 3 if we go with this normal instruction set. Alternatively, if the target machine has increment instruction INC. INC is nothing but it is also an instruction, increment instruction. So if our target machine contains this instruction means we can directly write INC A. So INC A will provide what? It will provide A equal to A plus 1 expression only. So this, using this increment operation, using this INC instruction set will execute efficiently, and also it will execute at a faster manner with low cost compared to this instruction set. Okay, so the selection of instruction set also plays a vital role in code generation process. Next, register allocation. Instruction evolving registers are shorter and faster. So two subproblems are there. One is register allocation and register assignment. In register allocation, it select the set of variables that will reside in registers at a point in the program. That is called as register allocation. So what variables we should store in the register, that is determined by register allocation. Then register assignment is nothing but we pick one specific register where a particular variable will reside in. That is called as register assignment. So certain machine requires register pass for some operands and results. See, for example, for this 3 address code, A plus B star C by D. So how a 3 address code will be? First, A plus B will be added and stored in a temporary variable. Then with that temporary variable, we will multiply C, and the result of that is stored in another temporary variable. And finally, with this result, we will divide D, and the result will be stored in the temporary variable. Okay, the final temporary variable, this T, will contain the final result. What would be the optimal code for this 3 address code? So first, we will load into the accumulator. LDA is nothing but load into the accumulator. So what we will load? We will load A into the register R1. Okay. Then we will add. So now register R1 will contain what? Contain A. So with A, what we have to do? We have to add B. So B is added. Add R1 comma B. Okay. Now what R1 contains? R1 contains the result of A plus B. A plus B. So with that result, what we have to do? We have to multiply C. So we are going for the instruction mul R1 comma C. Okay. So with the result of R1, we are multiplying C. Okay. So R1 contains what? Now R1 contains A plus B star C result. Then with this result, what we have to do? We have to divide D. So we are using opcode div. So div stands for division operation. So div R1 comma D, that is with the result of R1 we are dividing D. So finally what we have to do? We have to store the complete result. So the complete result of this expression is stored where? It is stored in R1. So this has to be stored in another variable, because always the register won't contain the final result. The final result will be allocated to a variable only, because that registers has to be used for performing another operation, right? So a register is used for storing the temporary result only. The final result will always be stored in a variable, right? So the result of R1 will be stored in T. For that we are using store opcode. So this is the optimal code used for performing this expression. Okay. So what it means wherever we need to store a value of a variable, we will use registers, and the registers is used for performing the operation, and finally the value that is stored in the register has to be assigned to a variable. Okay. Next, evaluation order. See, evaluation order uses the efficient order of evaluation and computation, and it also helps to reduce the number of loads and stores operation, and it also improves the speed of the code generation. Some computation orders require fewer registers to hold intermediate results than others. For example, see here, A equal to B plus C. How we will write a target program for this expression? First we will move B to register R0. Then we will add C with register R0. Then finally we will move the value that is present in register R0 to A. And for this expression, we will move value A to register R0. Then we will add E to the value that is stored in register R0. Then finally we move the result that is stored in register R0 to D. So in this example, the fourth statement, that is move A, R0, is redundant, isn't it? Because see, in the previous statement, in the third statement, already the value of A is stored where? It is stored in R0 only. So once again, reassigning the value to R0 is inefficient. So this particular statement could be removed. Using this statement is very redundant because already R0 contains A value only. It is not necessary to once again reassign the value to R0. So by eliminating this particular statement, we can make our generated target code efficient. Next, in this example, A equal to A plus 1, already we have discussed this example. First we will move A to R0, then we will add 1 to R0, and finally we will move the value of R0 to A. So instead of writing these three set of instructions with a total cost of 3, we can write a single instruction INC A. So INC A takes lesser time as compared to this set of instructions because it takes 3 cycles for each instruction, but this INC A takes only 1 cycle. Therefore, we should use INC A instruction in place of this kind of increment expressions. Okay. Next, target machine. So the target machine should generate the correct code. It should perform the desired task, and it should also be error free, and the target machine and the instruction set are prerequisite for designing a good code generator. Okay. So the target machine have the following characteristics. The first is it is byte addressable machine. That is, byte addressable is nothing but 4 bytes is equal to 1 word, and it also uses registers for performing the operations. N registers are used starting from R0 to Rn. And another important characteristics of target machine is it has 2 address instructions. So that instruction is of the form OP. OP is nothing but the opcode, source and destination. So OP is nothing but opcode. Opcode is nothing but the operation. And what is the source variable and what is the destination variable. So this is the 2 address instruction form. So the address modes together with their assembly language forms and associated costs are represented in this table. If the address mode is absolute, it will be of the form M, and address is also M. M is nothing but memory, and the cost for performing this operation is 1. Example is odd R0, R1. See here, 2 registers are involved. Both are memory operations, right? Then if it is a register address mode, it is of the form OR, and address is also OR, and cost is 0. So the example for this is add temp, R1. A temporary variable will be used, and R1, the value that is stored in the register R1, will be used. Such a kind of addressing mode, cost is 0. Then for indexed addressing mode, it is of the form C of R. Address is nothing but C plus contents of R. The cost for us is 1, and example is add 100 of R2, R1. Okay, this 100 is nothing but a constant value. And for indirect register, it is of the form star R, and address is contents of R. The cost for this is 0. Example is add star R2, R1. Then for indirect indexed addressing mode, it is of the form star C of R. The address is contents of C plus contents of R. The cost is equal to 1. So example is add star 100 of R2, R1. And for literal addressing modes, it is of the form hash C. The address is C, and the cost for it is 1. add hash 3 comma R1. That is, we are adding a constant to the value that is stored in the register. These are the various kinds of addressing modes and the associated cost, where M represents the operands that are stored in memory and R represents the operands that are maintained in registers. Next issue is instruction cost. See, cost corresponds to the length of the instructions. The cost of an instruction is given by this formula, that is, it is equal to 1 plus cost associated with the source and destination address modes. So that is called as cost of an instruction. For example, for this instruction, this is what? This is register oriented instruction. So what is the cost? It is equal to 1. Already we have discussed in this table, right? For different kinds of instructions, what is the cost we have discussed. So accordingly, if it is a register oriented instruction, both are associated with registers. So memory operations are involved. So the cost is equal to 1. And move R1 comma M. See here, register and a memory is used. So for this, the cost is equal to 2. Then add hash 1 comma R1. See here, we are adding a constant value with the register value. So the cost is equal to 2. And here we are subtracting 4 of R1 comma star 12 of R1. So this is equal to indexed addressing, and for this the cost is 1, and this is equal to indirect indexed addressing, and for this the cost is equal to 2. So for both 1 plus 2, the cost is, overall cost is equal to 3. Okay. So the total cost for this instruction set is equal to 1 plus 2 plus 2 plus 3. That is equal to 8. Next, for this instruction, first move B comma R0. So what is the cost? So a register and a variable is involved. So the cost is equal to 2. And here also a register and a variable is involved. A cost is equal to 2. And here also a register and a variable is involved. So the cost is equal to 2. So total cost is equal to 2 plus 2 plus 2, 6. Next, for this, move star R1. So this is a indirect register addressing mode, and star R0. So this is also a indirect register addressing mode. So the overall cost is equal to 1, and for this also the cost is equal to 1. So the total cost is equal to 2. And here both are variables. Okay. So here registers are not involved. Both are variables. See here, move B comma A. So B comma A cannot be directly performed because we have to first move any one of the variable to the register, and from that register only we will move to another variable. So it involves 2 memory operations, and this also involved some 2 memory operations. So the overall cost for this instruction is equal to 6. Okay. For example, how this instruction will be performed? First we will move B to R0, then we will move A comma R0, and finally we will move R0 comma B. So totally how many instructions will be involved for this particular target code? 3 instructions will be involved for performing the operation. So the cost for this particular one is equal to 3. And for this also, since both are variables, we will involve once again registers to it. So for this instruction also we will need 3 instructions. Okay, so totally 3 plus 3, 6. Cost of this instruction is equal to 6. The alternative approaches for the execution of the target code are interpretation of the source code, interpretation of the pass tree, interpretation of the 3 address code, and translation into virtual machine instruction. So these are the alternative approaches for executing the target code. Next, let us discuss about the runtime storage management. The code generated by the compiler must refer to the data objects using their addresses, so which must be resolved during the compilation process. So the addresses of data objects depend on the organization in memory. At runtime, the name should be mapped to the storage in the machine. The allocation and deallocation of memory is handled by runtime systems only. It is to manage the activation of procedures. Okay, so the execution of each procedure is called as activation. Information during an execution of a procedure is kept in a block of storage called activation record. So activation record contains what? It contains the overall information about how a procedure has to be executed. Storage for names and local to the procedure are also stored in this activation record. So the generated codes should be managed by this activation record during the runtime. Two standard storage allocation strategies are there. One is static allocation, another one is stock allocation. Static allocation, the position of an activation record in memory is fixed at the compile time only. And in stack allocation, new activation records are pushed onto the stack for each execution of a procedure. Here it is stored in memory, activation record is stored in memory, and here the activation record is stored in the form of a stack. Runtime allocation and deallocation of activation records occurs as a part of the procedure call and return sequences. So overall, the following are the actions that are performed while calling a procedure. That is, a call to a procedure is made, then return, then halt and action. So these are the 4 actions that are performed while executing a procedure. So usually runtime is divided into areas of code, a static data and a stack. So this is how a runtime memory will be divided. First, let us discuss about static allocation. See, in a static allocation, when a call to a procedure statement is executed, move instruction, MOV, okay, move instruction will save the return address and go to P. Go to P is nothing but this statement will transfer control to the desired target code location of the procedure P. So call statement in intermediate code is implemented by a sequence of 2 target machine instructions. One is move #here plus 20, callee.static area. So this saves the return address. This instruction helps to save the return address and go to callee.code area, and this transforms the control to the target code for the called procedure. Okay, here we are having 2 attributes, callee.static area and callee.code area. So these are constants. These refers to the address of the activation record and the first instruction to the called procedure. Okay, so it refers what? It refers the address of the activation record and the first instruction of the called procedure. And here we are having #here plus 20. So the source #here plus 20 in the move instruction is nothing but it is a literal return address. That is, it is the address of the instruction following the go to statement. Okay, then the code for the procedure ends with the return to the calling procedure, except that the first procedure has no caller. So its final instruction is halt, which return controls to the operating system. Okay, so a return from a procedure callee, is implemented by what? Implemented by goto.callee.static area. So which transforms the control to the address saved at the beginning of the activation record. Okay, see here, for example, so this is a simple instruction. First the code statement begins, that is action 1. Then we move #140, 364. So this move #140, what is here? It is equal to move #here plus 20, right? So what is the use of this instruction? It helps to save the return address. So where the return address is stored? Return address is stored in 140. Then go to 200. So where we will go? We will go to 200. So this is nothing but it transfers the control to the target code for the called procedure. Okay, so this transfers the control to action 3. And here the code for procedure. This is the actual code for the procedure call. This is the code where the called procedure statements will be there. And after it we are having go to *364. So what this means? Go to callee.static area. If a static area is given, So this transfers what? This transfers the control to the address saved at the beginning of the activation record. That is, it returned to address saved in the location 364. Okay. So this go to star callee.static area. If an instruction is in this manner means it means nothing but it transfers control to the where? Control to the beginning of the activation record. In the beginning we will have some address, right? For the activation record, it will transfer control to that place. In this case, go to star 364 means it returns to the address that is saved in the location 364. And 300 to 363 will holds the activation record for this particular code, and 304 will contain, this is the final statement, right, for this code. So this contains the return address. And 364, from 364 to the rest of the code also it holds the activation record for some procedure, and 368 will contains the local data for P. What is to be concentrated in this static allocation is two kinds of instruction. One is move instruction, another one is go to instruction. So move instruction always helps to save what? Helps to save the return address, and go to instruction will always helps to transform the control to some procedures. Okay, if an instruction like go to star some variable, some constant value is given, so that helps to return to the address that is mentioned in that static area, callee.static area. So this is what static allocation is. Next, let us see about stack allocation. So stack allocation uses stack data structure to store the activation record. The position of the activation record for a procedure is not defined in anticipation of runtime. So this position is usually stored in a register called SP, that is stack pointer. So SP points to the beginning of the activation record on top of the stack. So when a procedure call occurs, the calling procedure will increments the static pointer and transfers the control to called procedure. After control returns to the caller, it decrements the stack pointer, thereby deallocating the activation record of the called procedure. Okay, see, when we are calling a procedure, immediately what the stack pointer will do? The stack pointer will increment the address of the calling procedure. After the operations are performed in the called procedure, it will the control will be returned back once again to the place where a procedure call is made. So in that case, the stack pointer will be decremented, and the memory that is allocated for the activation record for executing the procedure call will be removed. Okay, let us check with an action codes. So the code for the first procedure initializes the stack by setting stack pointer at the start of the stack area in memory that is given by this instruction move hash stack start comma sp. So this helps to initialize the stack. And the code for the procedure, first procedure will be written. Then halt. Halt is used for determining the termination of the execution. So procedure call sequence increments the stack pointer, saves the return address, and transfers control to the called procedure. So that is represented in this instruction set. First we will add hash caller.recordSize comma sp. So this particular instruction helps to increment what? Increment the stack pointer. Then we will move hash here plus 16 comma star sp. This is used for what? Always move instruction is used for saving the return address. Then go to callee.code area. So this is used for transferring the control to the called procedure. So the record size is nothing but the record size is equal to the size of the activation record. Then return sequence. So here the return sequence has two parts. The called procedure first transfers control to the return address using this go to star 0 of sp. So it is used for return to the caller. Then the second part of the return sequence is in the caller, which decrements the stack pointer, thereby restoring stack pointer to its previous value. So the instruction for that is sub hash caller.recordSize comma sp. So this is used for what? This is used for decrementing the stack pointer to its previous value. Let us check with an example. See, first, this is the example given, code for S. We are having an action 1, then we will call Q, then action 2, halt. Then code for P, we are having some action 3, we return. So these are the two sets of code. First we will discuss how a code for S is made. First what we will do, we will write the move instruction, move hash, we will provide any address value. Okay, as of this example I have given as 600, so this is nothing but the stack starts at this address only, has 600 comma sp. So the stack pointer is initialized to the address value 600. Then the statements of the called procedure will be executed. Then after that what we will do, the procedure call will increments the stack pointer, right? So it has to increment the stack pointer and it has to saves the return address and it has to transforms control to the called procedure. So for that first we will write this instruction, that is add hash caller dot record size comma sp. So this s size is nothing but this is size of the activation record, okay, comma sp. So this is helps to begin the call. Then move hash 152 comma star sp. So this is used for saving the return address, and go to 300. So this is nothing but it makes a call to another instruction, another procedure, go to 300. Okay, so this will call what? This will call the code for P, the procedure call. Next, after that what we will do, so after the called procedure transforms control to the return address, what we will do, we will have to subtract we have to decrement the stack pointer value. For that we will use this instruction sub has s size comma sp. While calling we will increment the stack pointer, add has s size comma sp, and while returning we will decrement the stack pointer sub has s size comma xp. Then some code statements will be there. Then finally we will halt the instruction. So this is what? This is the code for S. Next let us see the code for P. Action any number. First we will increment the stack size. There we write S size, here we are writing Q size comma SP. Just for differentiating I am writing like that. But here actually the size of the activation record will be given. Then move hash 344 comma star SP. So this is used for what? This is used to save the return address. Then we will go to 200. That is the called procedure will transform the control to the return address. Using this instruction, then we will subtract what? We will subtract the stack pointer, decrement the stack pointer using this instruction. Then some action will be, some code segments will be executed. Okay, so this is the way by which a call to the procedure will happen using stack allocation. Okay, once again we will add Q size comma sp, and we will move some value, we will increment the stack pointer. Then this shows the return address where after calling the procedure it has to return. After the procedure is returned, the stack pointer is decremented. Okay, and this is for action 6. Action 6 is, this is another call to a procedure. Okay, and whenever a procedure is called, we will set or we will increment the stack pointer. Then we will store the return address. After executing the procedure, it will return to the place where the procedure is called. After the procedure returns, the stack pointer will be decremented. This set of instruction helps us to gain knowledge of how a procedure will be called and executed using stack allocation storage strategy. Okay guys, I hope you have understand the examples. Since these examples are written in assembly language codes, it is very difficult to understand. But if you understand the instruction sets that are given for each and every operation, the same thing is written in the example also with some memory values. Okay, so in today's class, as a summary, we have discussed about the issues that were present in a code generation phase and how a runtime storage management is performed using static allocation and stack allocation strategies.
Okay guys, let me meet you all with another interesting lecture. Bye-bye.